Let's walk through an example demonstrating the other type of chi-squared test. From experience, this is not a chi-squared test that appears a lot in the published research literature, at least not as frequently as the more common chi-square test of independence. Again, the chi-square test you are most likely to use is the chi-square test of independence, and we saw two examples demonstrated previously. What we will do here is demonstrate a chi-square test of goodness of fit. With the chi-square test of independence, we are examining if there is a relationship between two categorical variables. One of our previous examples looked at the relationship between the type of crime and whether the victim knew the perpetrator or if the perpetrator was a stranger. The null hypothesis assumes there is no relationship. If the NHST leads to rejecting the null hypothesis, then this leads to the conclusion that there is a relationship between the variables. Said another way, with our previous example, if there is a relationship, then the percentages for whether you knew the perpetrator or not would be different for different crimes. The chi-square test of independence is similar to most of the NHSTs we've seen prior. That is, the claim is usually in the alternative, and our goal is to reject the null in order to support our claim. The chi-square goodness of fit test is one of the less common NHSTs. This is the type of NHST where the claim is often expressed in the null hypothesis. In truth, this is probably part of the reason it doesn't show up as often in the published literature. As a quick aside, let's revisit an earlier problem. In particular, a problem that has the claim in the null hypothesis. This is the problem where you are trying to determine if a certain subjective measurement instrument is reliable. That is, if different people use this instrument, will the results generally be the same for this, our claim, is that the instrument is reliable. But, converting this to a pair of hypotheses for an NHST, we would best express the claim by saying that my ratings and my colleagues' ratings are the same. Obviously, this is a condition of equality, and in turn, this should be expressed in the null hypothesis, as it is here. Again, it is uncommon to have the null hypothesis as the research claim, but there are scenarios where it does happen. If we want to be mathematically formal, we could write that my average rating is the same as my colleague's average rating. M sub 1 equals M sub 2, where 1 represents my ratings and 2 represents my colleagues. And we clearly see the condition of equality here. Then, the alternative would be that the ratings are different on average. What makes this uncommon is that for most NHSTs, we have the claim expressed in the alternative hypothesis. So we want to reject the null. But if the claim is the null, then we don't want to reject it, i.e., we want to fail to reject the null. It would be nice to quote-unquote accept the null, but that isn't one of our options. So, the support of our claim would be a non-significant finding, a p-value greater than alpha. Note, this does not prove my instrument is reliable, but if we obtain a p-value greater than alpha, we fail to provide evidence that contradicts that claim. Unfortunately, the best we can do in an empirical science framework is to fail to reject the null. Thus, I can never prove that my rating is the same as my colleague's rating, but I can provide evidence that suggests my claim of reliability is not an unreasonable conclusion. Talk about a statement with a lot of double negatives. If, on the other hand, we get a p-value less than alpha, then we reject the claim, and this is something of a problem. This means we have definitively proven, under the NHST framework, our claim to not be correct. That was a quick aside, but the point is that the chi-square goodness of fit always looks like this also. Under most circumstances, we want a statistically non-significant result. Here's our example. We want to explore whether babies prefer primary colors, or if babies prefer to look at one color versus another. This is simulated data, but it is modeled off of previous studies that explored similar concepts. The idea is that we have 3 to 6 month old babies laying in their cribs, and we have the ceiling painted by quadrants in vibrant colors, red, green, blue, yellow. Then using some type of non-distracting eye tracking tool, we monitor where the baby spends most of their time looking. So the data records the color that the baby looked at the most while laying in the crib for a fixed amount of time. The researchers' claim was that babies at a certain age, say 3 to 6 month old babies, do not prefer one color over another. So if there is no preference, what proportion of the babies would have spent more time looking at the blue block on the ceiling? Well, if there are 4 options and there is no preference, then it should be an even split. A quarter, a quarter, a quarter, and a quarter. So by random chance, 1/4 of the babies tested would probably look at each of the different blocks. To convert this to a mathematical representation, we would say that each color is equally likely to be chosen. Thus, the proportion of babies looking at the green block is the same as the proportion looking at the blue block, is the same as the proportion looking at the red block, and in turn is the same as the proportion looking at the yellow block. Well, the alternative is a bit trickier. Remember, the alternative has to be the opposite, but it has to be exhaustive. Well, there are lots of ways to write the opposite scenarios of this, but the aspect that is similar in every possible example that is the opposite of this null hypothesis, and that is that they are all not equal. Or there is at least one proportion that is not equal to all the others. This means all 4 values could be distinct and different, for example, 10%, 20%, 30%, and 40%. Or maybe 2 pairs are equal, but the pairs are different, e.g. 2 at 20% and 2 at 30%. Or 3 are the same, and 1 is different from those 3. It could be green, red, and blue all are 30%, and yellow is 10%. The point is that there are lots of ways we might express the opposite of the null, but there is only one way that they can be all entirely equal. So let's look at the data. The data is summarized in columns B and C. Technically, this is an FDT, a frequency distribution table. We have that 21 babies focused primarily on the red patch on the ceiling, 11 focused on the green patch, 18 focused on the blue patch, and 10 focused on the yellow patch. If you add this up, you get a total of 60 babies. Now, if the null hypothesis is true, we expect the proportions to be the same. Or in this case, we expect the same number of babies looking at each block. So in this case, we would expect there to be 15 babies for each color. Let me stress that this is not a contingency table. There really is only one variable here, the color choice, and the column is the frequency. We just happen to have 2 frequency columns, an observed frequency column and then an expected frequency column, where the expected values are just the numerical manifestations of our null hypothesis. So the expected values are essentially our null hypothesis in this case. Remember, we can talk about the difference between 2 numbers, but once you have 3 or more numbers, you can't talk about the difference of the numbers. Similar as to our previous 3x2 test of independence, we can't just subtract numbers. But we can calculate a CHISQ.TEST statistic using the squared residuals for our expected frequencies. This is what makes the CHISQ.TEST statistic so useful. Fortunately, the squared residuals are calculated in the same fashion. We take the difference between the observed and the expected frequencies, we square this difference, and then we divide by the expected frequency. The chi-square statistic then is the sum of these squared residuals. For this problem, we get a chi-square of 5.733 and change. The degrees of freedom for a chi-square goodness of fit is always 1 less than the number of categories. So here, the degrees of freedom are 3 because there are 4 categories. Plugging these values into the CHIDIST function in Excel, the CHIDIST function, we get the p-value of 0.125 and change. Well, this p-value, this would be larger than any reasonable alpha we might pick. Even a generous alpha of 0.1, this is still bigger. So the conclusion is that we would fail to reject the null. But our null was that the proportions were equal, so we are not rejecting this. This is not the same thing as accepting it, but it is still better than rejecting it. So the researcher's claim might be true, or at least we haven't disproven the researcher's claim. So from the flowchart, does the original claim contain the condition of equality? Well, it was a bit convoluted, but yes, our claim was expressed in the null. Next, do we reject the null? No, we fail to reject the null, so we go down this path. So there is not sufficient evidence to warrant rejection of the claim that the proportions are the same. Not rejecting, that means we're keeping it, but we're not keeping it in a way where we are saying it is true, we're just not getting rid of it. Again, there is not sufficient evidence to warrant rejection of the claim that the babies don't prefer others. Again, not rejecting is kind of like keeping, but we are doing it in a most non-committal way. I always associate this with a wedding proposal that is met with the response, well, I don't want to not marry you, instead of just saying yes. I'm not sure that this is the response anyone proposing actually wants to hear. Again, there are two ways to run this test. The first is to run everything in the first 14 rows as shown here. The second is to calculate the expected frequencies and enter these in the CHISQ.TEST function. That's CHISQ.TEST. This is shown here in row 15. Feel free to use this shortcut function if you are comfortable with what must be entered and what the Excel function returns as an output. But the one key thing to remember is that this template is set up for a goodness of fit with 4 categories. If you had 5 categories, you would need to add a row and adjust the overall worksheet accordingly. The top part assumes that they are all equal. Thus, the top part of this template calculates all of the equal frequencies for you. But it could be the case that you want to impose a different set of proportions for a different null hypothesis. And for the expected frequencies in this lower NHST, the null hypothesis is that the proportion of red and blue are both 40%, while the proportion of green and yellow are both 10%. This is sort of like testing the claim or the hypothesis that the babies prefer dark primary colors to other colors. But the claim is structured with a very specific percentage for that preference. In this case, I would have to enter the percentages from the null hypothesis, and using the total sample size in these percentages, Excel will calculate the expected frequencies. Instead of saying they are all equal, here we are giving a specific portion for each value of our variable. And this is where the term goodness of fit applies best. We are trying to see if the data and our hypothesis fit well together. I believe the percentage breakdown looks like this, and I'm wondering if my data will fit well with these proposed proportions. Well, the p-value for this is 0.033 and change, and if we are using a conventional alpha equals 0.05, we would reject the null, which suggests that our data is unlikely to occur if the proportion breakdown was indeed as we hypothesized. Said another way, we have failed in our attempt to show that the data is indeed a good fit for our hypothesized model. The goodness of fit failed. This is often the test that is used for multinomial experiments. These are just like binomial experiments, but we relax the requirement of there being only 2 outcomes, and we allow for 3 or more outcomes. Further exploration of this topic will have to be left for another time.